Alright, in this video we look at an example of a a surface integral of a vector field. So the notation here is we're looking at a double integral across a surface. There must be some sort of vector field given, and then we need to dot product that with dA, where dA is the oriented little part of the surface, and what we mean by that is that dA is the cross product of the surface parametrization, the cross product of the derivatives of the surface parametrization, which gives a vector that points normal to the surface, and then that is being multiplied by the area element du dv. Okay, so if we're going to look at this problem, we have a certain vector field f of x comma y comma z. So we have a vector field is x comma y comma z, and we've seen this vector field before. It's this vector field that is basically an explosion vector field. So there's some sort of zeros over here at 0, 0. There is an explosion that's happened, and right here, these blue arrows, these are the vector field as they're coming from the surface, coming through this surface. Okay, and then we can see here these red vectors. These red vectors are dA. dA are these red vectors, so it's RU cross RV. That's the normal vector to the surface, and then it is multiplied by a normal vector essentially times the area of that little part of the surface. So this is what's called an oriented area. This is oriented area. Okay. So if we're going to do the flux integral, this surface integral of a vector field is also called a flux integral. If we're going to compute this flux integral, we first need to know which part of the surface that we're talking about. Okay, and we can see that it's the outward portion of the surface cut by the planes z is equal to 0 to z is equal to a. And what that means is that we have a cylinder that is extending in the z direction. So one of the parameters has to be our height. So if we parameterize this surface r of u comma v, it looks to be a cylinder of radius 1. So we'll have cosine of v, sine of v, and then our other parameter u will be the height variable. Okay? And we have seen in the past videos RU cross RV, I think comes out to be negative cosine of v, negative sine of v, comma 0. We'll double check that in just a second. Okay. And then if we want the flux as it's coming through only part of the surface, here we can see this orange surface here. It's not the whole cylinder, but it looks to be part of the cylinder. Okay, and that means that we're going to have to put a restriction on the angle V. Maybe the angle goes from 0 to pi. Maybe we've only got half of the cylinder. Okay, and we just care about figuring out how much of the vector field is crossing through this part of the surface. Okay. All right, so we can now set up that integral. Okay, because we have our vector field. So we would need the vector field at those points on the surface. And because our surface is x is equal to cosine of v, y is equal to sine of v, z is equal to u, wherever I see the x in my vector field, I'm going to put cosine of v. Wherever I see the y in my vector field, I'm going to put sine of v. And wherever I see a z, I'm supposed to put u. So here is our vector field along the surface. We need to dot product that with the normal vector to the surface. And we can double check that computation now just to make sure that we're remembering it correctly. So our surface parameterization of the cylinder is cosine V is the angle variable, sine of V, and because the cosine and sine are in the X and Y entries, U is the other parameter for Z, and then we can take the derivative of this surface with respect to U and cross product it with the derivative in the V direction, R of U comma V in the V direction. And as I suspected, minus cosine of V minus sine of V, 0. Okay, so if we take that vector and dot product it with cosine of V, sine of V, U, if we take these two vectors and dot product them together, okay, Jason, you will get minus cosine squared minus sine squared, which if you simplify that, should come out to be minus 1. Okay, so there we have it. When we do the dot product of the vector field and the surface, we get a double integral of -1 du dv, and u is going from 0 up to a because they want it to go up to a plane, and v is the angle, and we want that to only go through half of the cylinder. Okay, so that is a pretty easy integral to compute. It would be -a multiplied by pi. Okay, and the negative sign is indicating that there is more of the vector field is passing through or into the surface, going inside of the cylinder that is coming out of the surface. So we can see here that some of these vectors are, the vector field is pointing outward, right? We can see the direction of some of these vectors, they might be coming through the surface this way. So when we're adding up all the vectors crossing through the surface, there is more going in than there is coming out, and that is how we are interpreting the minus sign there.